Right, so now I want to turn to superstrings. As I mentioned earlier, there are precisely five consistent superstring theories, all in 10 space-time dimensions. These are given the names 2A, 2B, type 2A, type 2B, type 1, and two heterotic theories, which are called HO and HE. In each case, we can, each of these has supersymmetry. So these, this one has 1, 1 supersymmetry, this has 2, 0 supersymmetry, and these all have 1, 0 supersymmetry. So what this means is that in 10 dimensions, the supercharges are Majorana Weyl spinors, which are the Majorana piece means that they satisfy a reality condition, so that in suitable conventions they can be taken to have real components. And the Weyl condition means that they are chiral spinors. In 10 dimensions, there's an analog of gamma 5, which is gamma 11, and spinors can be chiral, in other words, eigenvectors of gamma 11 with either chirality +1 or chirality -1. In this case, the 1, 1 supersymmetry means that there's one right-handed supercharge and one left-handed one. In the 2B case, there are two left-handed supercharges and no right-handed ones. And in this case, there's one left-handed supercharge and no right-handed ones. Of course, there's a matter of convention as to whether one has 2, 0 or 0, 2. In those two cases, one gets essentially equivalent theories. And there's a gauge group in each case. Here it's simply U1. In the case of type 1, it is, here there's no gauge group, here it's SO32, and in the HO case it's SO32, and in the HE case it's E8 cross E8. So the choice of possible gauge groups is fixed by anomaly cancellation. Long ago, Green and Schwartz showed that anomalies, that such theories are typically anomalous, and the anomalies only cancel for these specific groups, and also the case of the abelian group U1 to the 496. But these ones give the non-trivial interacting theories, and in the case of, in each case, there's the massless modes are governed by a supergravity theory, which is for the 2A or 2B is the 1, 1 or 2, 0 supersymmetry, supergravity, and for these ones with the 1, 0, it's for the 1, 0, it's a 1, 0 supergravity plus super Yang-Mills with gauge group SO32 or E8 cross E8. And these have a number of remarkable properties. They're tachyon free and they appear to give consistent quantum theories. And as I mentioned, there are 5 distinct quantum theories which emerge in this way. So what I want to do is start addressing the question of under what circumstances these is the possible duality symmetries of these theories. And as I mentioned, there's issues if one's looking at non-perturbative duality theories. There's a problem, symmetries. There's a problem of that one can't, well, the theories are defined by perturbation theories for weak string coupling, and one doesn't know how to extrapolate them to strong string coupling. But it turns out that there are some things which are protected by supersymmetry. We have a large amount of supersymmetry here. And these supersymmetries there are some things which are protected by supersymmetry and get no quantum corrections, and are things which can be extrapolated from weak coupling, where we understand the theory, to strong coupling, so that what we know about the theory at weak coupling will tell us about what must be going on at strong coupling. So the first of these is the low effective action, which I'll just write as EA for effective action. So in each of these theories, the theory of the massless modes will be governed by an Einstein term plus corrections involving the string in principle, you get higher derivative terms, which I've written some for the gravity theory. We'll get terms involving the square of the Riemann tensor, the fourth power of the Riemann tensor, and so on, with more and more powers of the string length to get the dimensions right. But at low energies, we can ignore the higher order curvature terms. So at low energies, ignore so these are suppressed by powers by the string length, and the string length is very small. So unless we're dealing with very high curvatures, these, and hence related to high energies, these will all be suppressed, greatly suppressed. And at low energies, at energies much lower than the string length, so we're talking about energies much less than 1 over the string length, we can ignore these, and we can also ignore the massive string states. The spectrum of the string, as we've seen, will start off with some massless fields plus an infinite tower of massive string modes, all with masses of the order of given by the string mass, which is 1 over the string length. And at low energies much smaller than that, we can ignore these and consider an effective action, which will be 2 derivative for the bosons and 1 derivative for the fermions as usual, plus for just the massless and the remarkable thing is that this effective action is uniquely fixed or determined by supersymmetry and choice of the gauge group. And the choice of the gauge group was highly restricted by the anomaly cancellation. So if we're looking at the 2A theories of the 2A string theory, then the effective action is uniquely fixed by the supersymmetry, and similarly for the 2B and so on. And that means that it will not, the form of the action will not receive any quantum corrections, and will be something which could be extrapolated from where we know about it for the weakly coupled string theory to the strongly coupled string theory. So so in particular, any symmetry of the full must also be a symmetry of the effective action. So the duality symmetry we're going to be looking for will be a subgroup of the symmetry of the effective action. So we've already seen that in the context of what we're looking at in the bosonic string, which also, those details also will be feature for a subsector of the superstring. There we had that the symmetry of the effective action was a continuous group ONN, and the actual duality symmetry was the ONNZ subgroup of the continuous group ONN. So we have an infinite discrete subgroup. So it means that it's not a continuous group, it's a discrete group, but it's got an infinite number of elements, and it's a subgroup of this ONN. And so one of the things we're going to look at is symmetries of the full string theory of the effective action compactified on a torus or a Calabi-Yau space, and then we'll look for subgroups of that which are which are candidates for actual duality symmetries of the theory, and we'll see that the pattern is rather similar to this. We're looking at discrete subgroups with integer valued matrices as a subgroup of a continuous group. And the other feature I want to discuss, which is something which can be extrapolated, is what is known as BPS states. So what are BPS states? So these are states. So we have a supersymmetric theory where we have 16 or 32 supercharges. So if you have a 1,0 supersymmetry, you've got one Majorana-Weil supercharge, which has got 16 components. And if you've got the 2,0 or 1,1, you've got two Majorana-Weil spinors, so each of which has got 16 components, so you've got 32 components altogether. So let's call the total number of Qs S, which is either 16 or 32 for the cases we're looking at here. So if we consider a state phi, acting with the Qs, will generate multiplet. So if one starts off with a scalar, then acting with a 1Q will generate a fermion, a spin half field, and acting with another Q will give more fields. And you can work and see how spectrum that's generated that way. So first of all, if no Q's in other words, if any Q acting on phi gives a non-trivial state, then you get the maximal case, and you get a little bit of work shows that this generates a multiplet with 2 to the S over 2 states. And the way of seeing that is, if you look at the superalgebra, you find that you can, by change of basis, you can bring it to a form which is essentially a Clifford algebra, and a Clifford algebra generated by SQs would be, if we think of the Qs as being realized by gamma matrices, then we end up with a representation of these gamma matrices with 2 to the S over 2 states. So the details of that don't matter. It's just to say that we get a multiplicative of this kind. But if instead S minus P Qs annihilate phi, in other words, some of the Qs will leave the state invariant. They will, the change generated by Q will not change phi. Then we end up with a multiplet with 2 to the P over 2 states. And we call this a short supermultiplet, and the general, this one, the generic one, we call a long supermultiplet. And the higher, the smaller P is, then the less, then the smaller the supermultiplet. And I'll be particularly interested in the case where P equals S over 2, where half of the Qs annihilate the state, and these are said to be half BPS states. Now, so the states which fit into short multiplets are generically called BPS states for rather misleading historical reasons. And these have a number of properties. So ones with which are preserved by some number of supercharges. One is that the states are stable. We can show that the states they have the masses are given by a formula of the kind f, which is a function of the moduli, represented by scalar fields, and of a set of charges, which both of which we're going to talk about at more length. And this receives no quantum corrections. The stability follows from the fact that if we, one way of seeing that is that, sorry, I got an error message on the connection. I think it seems to be working now. So the mass of generic states is such that they'll have a mass which will be bigger than or equal to the value which is satisfied by the BPS states. So the BPS states are the ones with the lowest value for the charge, for the mass, and that's what leads to the stability. Also, they tend to be in short multiplets. They're in short multiplets by definition. And if one were to move away from masses satisfying this property, then that would involve jumping from a short multiplet to typically a longer one to one which has got preserved by less supersymmetries and hence will have more states. And because you'd expect the number of states to be preserved as you move around the moduli space, you wouldn't expect it to jump. That's another way of seeing that it's able to, it should not change. And in particular, the degeneracy, or the number of states of the BPS states, should be something which, again, is something which could be extrapolated from weak to strong coupling. And all that goes together to show that if we were to, the BPS spectrum, the set of BPS states, can be from the perturbative region to the whole another way of saying that is that if state with the BPS state with charge Q coupling it will exist of the coupling and for the whole So if we were to find a BPS state with a particular set of charges at weak coupling, then a state with those charges will exist for all values of the moduli. We can extrapolate the whole moduli space. Of course, because the mass depends on the moduli as well as the charge, the mass will typically change as you move around the moduli space, but it will always be given by this formula, and the spectrum will always be preserved. Although, or in other words, the set of charges of for which there are BPS states will be the same over the whole moduli space, but the values of the masses will depend on where you are in the moduli space. So we've seen some examples of that already, the momentum modes and winding modes for toroidally compactified string theory. There we had momentum modes where the mass was given by some integer over the radius, and the winding modes where the mass was given by another integer times the radius times the tension, with a 2 pi absorbed into that. So here we think of n and n primed are examples of the charges I'm talking about. The radius is the modulus. So it turns out that the momentum modes and the winding modes are half BPS states, if one looks at string theory on the torus. And so suppose we started off with a momentum as a state with winding number 1 at weak coupling, then if we extrapolate to strong coupling, if we extrapolate to other values of the radius, then it will exist. Instead of saying coupling, let me talk in terms of the radius. We know at large values of the radius that there are momentum modes with mass n over r, and for each n there's such a state. What this argument is telling us that we can extrapolate those states down to small values of the radius, and those states should still stay within the theory. And also, more importantly, that just as importantly, that the winding states, which are very massive for large values of the radius, if they exist at large values of the radius, they can be extrapolated to any value of the radius. And that's very important for us because that means that we can extrapolate them down to small values of the radius in which they're becoming lighter and lighter. And so one could reliably say that that the arguments we had before were valid, that there's an infinite nut tower of massless states becoming massless as r tends to 0, and these are interpreted as the momentum modes of a dual circle, and that's play an important role in the establishment of T-duality. So I'll stop this part of the lecture here, and I'll continue in the next part.